Hello, everyone. Today I would like to share our new work, Polaris, which is a set of efficient, transparent, succinct zero-knowledge argument schemes. So our goal basically is try to provide the blockchain privacy. So currently we know there's many applications try to build on the blockchain platform. For example, decentralized finance, decentralized identity management schemes, and the supply chain, and so on. The reason is blockchain can provide trusted consensus, computation, and immutable data between untrusted entities. So in order to look at the privacy problem, let us look at in detail, look at the blocks and how they chained together. So this diagram here basically is one block, but they consist of multiple transactions. For example, here is 64 transactions. Then those we were using Merkle tree and generate Merkle root. So those part are header. Then we hashed and then hash value at put here. And this entry here is hash from the previous block. So then each block, because you hash the previous block, so that's how they connected. So blockchain basically is a linked list of blocks by hash chain. So how we can achieve blockchain privacy? In other words, how to share the sender, receiver, and transaction privacy. The tool used here is zero-knowledge proof systems. So for zero-knowledge proof system, in general speaking, basically those proofs are proofs that yields nothing beyond the validity of the assertion. You could do multiple communications. At the end, verifier only learned the validity of the assertion, nothing else. For example, if we put the prover, then we named as Alice, verifier we named as Bob, as general crypto system we usually setting. Then we have a statement here, Alice wants to prove to the Bob. It's like the claim that I have 1 Bitcoin, or could be I uploaded data for product, for example, organic salmon. And for the verifier, and he said, oh, this statement is true, but I do not know why. So formally, we have a definition. First property is completeness. So prover can convince verifier if the statement is true. And the second property is soundness. So in this case, is if the statement not true, and the prover cannot convince the verifier. And the third property is zero knowledge, which means the verifier learns nothing except for the validity of the statement. So in order to design a zero knowledge proof system for practical applications, we would like to consider those different factors. First is prover complexity. This is the computational cost for the prover to run the protocol. And run the complexity means the number of transactions between the prover and the verifier. And the communication cost, which is the total size of communication between the prover and the verifier. And the verifier complexity and the setup cost. Some schemes, like the zkSNARK used, they have setup cost for generate the common reference stream. And how about the integrated of computation? So what's the problem? So for example, Alice wanted to prove to Bob that the hash value y equal to hx is correctly evaluated without sending Bob the pre-image x, which means Bob only gets y. How he can know y is evaluated from the hash function h at the pre-image x? So like we see the blockchain structure, they basically always hash values there. So this is achieved by verifiable computation, which is done through representing an algorithm or a program as a circuit. So zkSNARK represents the zero knowledge succinct non-argument knowledge. Zero knowledge, as we have visited several times, does not leak any information about the witness. Succinct, which means proof size is independent of NP witness sizes. And non-interactive, which means only one message is sent by prover. And the proof is argument of the knowledge. Those are the existing schemes, just some of those. For example, QAP and QSP based. So first published in the GDPR 13 paper, so it's in the 2013, and later on in the BCT TV 14, and in 2016 was improved a lot. So this setup is a private setup, so you need a common reference string, and the security is based on knowledge of exponent. Okay, so they have many different implementations because Zcash basically is implement those schemes. And the second class is based on the hard problem, like the bonnet proof and the Spartan DL based on the computation infeasible ability of discrete logarithm. Okay, and the Merlin basically is a private setting, but their common reference stream can be updated, but they based on the stronger problem called the strong Diffie-Hellman problem. And the third class is public setting like Niagara, Stark, and Aurora. And they do not rely on the hard problem. Instead, just collision-resistant hash function and pseudo-random generators. Okay, so this is those recent ones. So now, then we restrict our concept to R1CS relation, which means we assume we already converted a algorithm or program into the circuit. And from circuit, then we convert it to a matrix. Okay, so a R1CS instance consists of those parameters. Basically, we have three metrics. I will show you right away. And V is the public input and output vectors of instance. And W is the private input vector of instance. And we also assume this in these three matrices, non-zero elements are bounded by N. So what's the relationship? Basically, you could think this is the left input of the circuit, and this is right input of circuit. So here we only consider multiplication gate. Then this is output. So basically, your output equal to left input multiplied by right input. So that's equal to 0. Then you have number of the gates. So that's why this is a vector. Okay. So the goal of the zkSNARK scheme is try to prove this relation. Okay. So R1CS is more general than the problem of arithmetic circuit satisfiability. So like I mentioned, so here basically three vectors represent the left input, right input, and output vectors of multiplicative gates in the circuit. And the witness W basically consists of circuit, the private input, and wire values. So for example, if we would like to prove any transaction, for example, UTXO model in Zcash, then we only need to prove to the miners this SHA-256 circuit has this relationship without reveal the value in X. Okay, so because X consists of those transaction values, right? And the cache implemented the GORS-16 to achieve this goal, to prove this. So for the Polaris, so we basically can instantiating this Polaris with different polynomial commitment schemes, and we can get the best one is public setup. In this case, we have prover's complexity the same as others, but we can make this concrete, like here, coefficient. What's this coefficient? We can explicitly get this one. Also, proof size, also bounded by the square of the log n, and the verifier complexity also the same. So those are logarithm complexity. And our efficiency is achieved using new efficient sparse encoding. And for the prover's cost, we can reduce from linear to logarithmic because we embedded zkR protocol into low-degree test. Also, we designed a new explicit computation circuit as the input of zkR protocol. Okay. So first we look at how we encoding R1CS relation. So basically you have two ways to encoding that. One is using the multivariate polynomial, another using univariate polynomial. So Polaris will adopt this. So this is the R1CS relation encoded as a polynomial. So you can tell this is left input, right input, output. So we want to prove this is 0 at every point, but it's turned out we can prove this product relation. Then which means that you see we have a circuit, we get a matrix, then we encode it as a polynomial. And this relation should be true in the small this region, but for every element in this region. Then it's turned out we can just evaluate it at random point, prove this relation at a random point. Okay, so that's the first product check polynomial. And the second will be the univariate sum check. So this is try to prove this three relationship. Okay, in order to prove this three relationship, so this means left input evaluated at random point, right input evaluated at random point. This is output evaluated at random point. So this is through this random linear combination. Okay. Okay, so that's in the here I just briefly introduce you structure of Polaris. Basically, Polaris has two sub-protocols. One is the product check protocol, another is univariate sum check protocol. So for the product check protocol, the prover first run the sparse encoding to get those three circuit polynomials. Then compute the product check polynomial. By division, get the fifth polynomial. Okay. Then we run the polynomial commitment scheme to commit GX. So this is where a set of the Polaris can come from by using different polynomial commitment schemes. So finally, we have part of the proof we call the pi1, which only have 5 elements in the field. Then for the verifier, they will verify this commitment, and verify the multiple, like the product relationship. If this is true, then they will run this univariate sum check protocol. So univariate sum check protocol is more complicated than the first one. So prover of verifier together run the no-degree test initial phase. So here I involve the verifier, but basically verifier just pick the random values. So by Fiat-Shamir transform, then we can make just prover pick up those random values. Okay, so that will be non-interactive. However, here for simplicity, I just write in such a way. And the prover runs a Merkle tree commitment to commit 2 Reed-Solomon cowords. Then they will run the zkR protocol 3 times because for each of those polynomials, input, left input, right input, and output. Then finally, they will run the no-degree test final phase, then generate second part of the proof, pi2, and this proof has a logarithmic size. Finally, verifiers verify the phi2 with the complexity, also logarithmic complexity. Okay. So we did our implementation, also compare with other known schemes. For the provers complexity, and those are all similar. But the Ligera, using Ligera is here. Spartan is the best. Spartan is the one using multivariate polynomial representation instead of univariate. Okay. And second is the proof size. So proof size is log square root of log n. N is the size of the circuit. And the Ligera, because the size is square root of n, in the small number of the constraint, and this number is, you can tell, it's already big compared with those log size case. And the last one is verifier's complexity. So verifier, so Polaris is here, and this is Aurora, and this is Ligera. Okay, so compare with Ligera and Aurora, and our provers, our verifier's complexity is greatly improved because we applied the zkR protocol into the low-degree test. So in this talk, I introduced the Polaris, which is a new zkSNARK scheme for a SHA-256 circuit, which is about 23 AND gates. If we want to prove or to verify the SHA-256 pre-image in zero knowledge with 128-bit security, then we have proof size less than 150 kilobytes, and verification time is less than 11 milliseconds. So those performance are competitive to all existing schemes. However, we have concrete verifier's complexity, not just bounded by that big O. So this is, I already mentioned, then the verifier's performance is much improved compared with Ligera and Aurora. Also, we only using the symmetric key crypto schemes. Then you have seen, in order to get those polynomials, how you get, basically is using Lagrange interpretation get polynomials. Lagrange interpretation corresponding to inverse fast Fourier transform. And the polynomial evaluation or Reed-Solomon coward generation, which corresponds to the FAT. So currently we try to re-implement our schemes by using coding approach, which is using linear feedback shift register. And for the blockchain security, and the I think that not many schemes have been implemented in the real world applications. So existing one is QAP based zkSNARK. Okay, although they have constant proof size and verifier complexity, but they need a large common reference string. Because this not common reference string vulnerability has been found in 2019 in Zcash's early implementation of GDPR 13. So currently they will implement the Guang 16. So Polaris basically it is within the set with transparent setup. So they have a post-quantum security, which can eliminate many vulnerabilities caused from computation of highway crypto operations. Of course, the Polaris verifier efficiency can find some potential applications in DeFi, such as repos blockchain and crypto solutions and supply chain management. Basically, we also extend our work to supply chain management, which is the work we have done before. Okay, so I guess that's all I want to say. So the work is taken from this paper. Okay, thank you.